Okay, here's the second part of our snapshot. In this part, we're going to have one additional condition that, if it is satisfied, makes problems associating intervals to percentage of data in that interval a little bit easier. If you remember, Chevyshev's theorem tells us that the relationship between the number of standard deviations to that of the percentage is given by 1 minus 1 over k squared, and that's what is associated with the percentage of data, correct? Well, if our data has what is called a bell-shaped distribution, and I've talked about this in class, so you should be familiar with it. If it has a bell-shaped distribution, then we have a little chart that we can work with that associates K, get my pen back, K, the number of standard deviations to that of the percentage. And so we don't have to worry about this messy formula that is associated with Chevyshev's theorem. Once again, we're either going to give the interval, so we'll find K and then the percentage, or we'll be given the percentage, find K, and then determine the interval. Here's our first example. Once again, I suggest that you stop the video, work the problem. The national mean for mathematics SAT scores in 2011 was 514. The distribution of scores was approximately bell-shaped, okay? I got this key word here, and I didn't, right there, bell-shaped. And the standard deviation was approximately 40. So I know my mean is 514. I know my standard deviation is 40. I want to know, what boundaries would you expect 68% of the scores to fall in? In other words, I want to know an interval that's going to contain 68% of the data. It's bell-shaped. So according to the empirical rule, we need to be within 1 standard deviation of the mean. Well, again, the distance is related to k times sigma. The distance is going to be 1 times 40. So our distance is 40. So if our mean is 514, and if we add 40 to that, we get 554. Pardon the writing here. If we subtract 40 from 514, I did it right, we get 474. So the interval 474 to 554 will contain 68% of the data. Once again, it was bell-shaped, so I was given the percentage. I found a number of standard deviations, but I need to get the distance, right? And the distance is related to standard deviations by that formula there, k times sigma. Moving on, next problem. Once again, stop the video, work it out, compare what you get to me, and hopefully I don't make a mistake, and you don't make a mistake. Citrus fruit consumption. The mean U.S. yearly per capita consumption of citrus fruit is 26.8 pounds. So I know the mean is 26.8 pounds. The distribution of fruit amounts consumed is bell-shaped. I love that word, bell-shaped, don't you? With a standard deviation of 4.2 pounds. I want to know the percentage of Americans that would be expected to consume between 14.2 and 39.4 pounds of fruit. In other words, I am given the interval. And I want to find the percentage this time. If I want to find the percentage, I need to find K, right? Notice in all these problems, I'm usually finding K, correct? And then I'm either using it to get the distance or the percentage. Well, here I have the interval. My mean is 26.8. The distance from the mean to an endpoint is 39.4 minus 26.8. That distance is 12.6. That's my distance. Now I'm trying to find K, but remember, K times sigma is equal to the distance. So K is equal to the distance divided by sigma, 4.2. Well, when you divide 12.6 by 4.2, you will clearly get 3. So the number of standard deviations my endpoints are, you can show it for this side too, okay? That is 12.6, so it's centered at the mean, but K is equal to 3. Since I'm talking about a bell-shaped distribution, I can work with my table. K is equal to 3, and it tells me 99.7% of my data, or 99.7% of the U.S. population will consume between 14.2 and 39.4 pounds of fruit next year. That's amazing. That's a lot of fruit. But it's good for you. So, what's the difference between our two methods, Chevyshev's and the empirical rule? Both of them are relating the percent of data to an interval, right? And that interval is centered at the mean. Chevyshev's works all the time, but is a poor estimation of that percentage. The empirical rule works when you have a bell-shaped distribution. So Chevyshev's relates K to the percentage by this formula here, right? Whereas the empirical rule, it has a table. Right? But both of them essentially work the problems in similar fashions. If you're given the percentage, you find K from this formula. If you're given a percentage, you find K from the table. And then you get the distance by this relationship, right? If you're given the interval, then you know the distance. If you know the distance, you can find K by this formula. You find K, plug it in here, you get the percentage. You find K, find in the list, you get the percentage. But the empirical rule, you must have bell shape. Got it? I hope this helps. I hope I didn't make a mistake. And I hope you can figure out and understand what I tried to get across to you. I really do hope this helps. So I encourage you to watch it and just let me know. Take any comments, criticism, advice, recommendations. Time's running out, so I'm going to let you go. Thank you.